Now it's a great pleasure to introduce Manuel Rivera, that is the first postdoc of the Miami-Centro collaboration. And he's going to be speaking about categorical and algebraic models for path spaces.
Well, thank you for the invitation. It's been fun, both mathematically and non-mathematically. It's been a good week. Okay, so first let me say a few words of what we do in this project and why we are interested in these constructions, okay? Why we do it. So we will use categorical techniques to obtain combinatorial models and algebraic models for path spaces. Okay, so by path spaces, I mean it in a broad sense. Path spaces might include some boundary conditions on the endpoints on the path, like for example, based loop spaces or free loop spaces, and so on. Okay, and our immediate purpose or what we have in mind are the following. So first, we're interested in extending certain results to connected, possibly non-simply connected spaces. Okay, so in the literature, there are certain statements relating, for example, the cobar construction, Hochschild complexes to spaces of paths, and many of these statements have the hypothesis of simply connectedness because they depend on certain spectral sequences arguments in which this hypothesis is required. Okay, so we want to generalize these results for connected, possibly non-simply connected spaces. We are interested in obtaining small models for path spaces suitable for calculations. We are also interested in understanding the algebraic nature of spaces or the algebraic nature of spaces with more structures, like manifolds, for example. So what do I mean by the algebraic nature of spaces? We're interested in statements of the form that relates the category of spaces to some algebraic category, right? For example, like E-infinity coalgebras with some model structure is equivalent to spaces with some model structure. Statements like that. And the same for manifolds. When you have a manifold structure, you also have extra algebraic structure. Can we describe this manifold structure purely algebraically? Okay, so that's also a motivating question that we have in mind. String topology is about free loop spaces on manifolds, okay, intersection type operations in manifolds. Once we have these models, we can recover these operations maybe algebraically or combinatorially and make explicit computations. We're also interested in obtaining transparent and concrete algebraic and combinatorial formulations for the notions of infinity local systems, which are like DG modules over chains on the base loop space. So if we have an algebraic model for the base loop space, we can use this algebraic model instead and describe what it means to have an infinity local system in terms of algebra, and also describe more concretely homotopy coherent nerve constructions. Another application that we have in mind is that once we have these algebraic models, it allows us to bring in tools from homotopy theory of algebraic structures and, for example, Koszul duality to all the above. Okay? Koszul duality is understood in the context of operads, of algebras, and we would like to apply it to, for example, string topology, or more topological problems, okay? And finally, we will also obtain models for higher categories suitable for different purposes. So this relates to what Kaledin was talking yesterday, okay? So this is what we do and this is what we have in mind, okay? Great. So the main results and constructions in this project follow from understanding the relationship between three functors. Okay? The first functor is the path category. So given a topological space, I can associate functorially a topological category. So a topological category is a small category in which the homesets are spaces and composition is a continuous map. So it's enriched over topological spaces. So what's the construction? So given a space, the objects of this category will be the points in the space, and the morphisms between 2 points will be the space of paths, right? And composition is obtained by concatenating paths. So by a path, here I mean a parameter r together with a continuous map gamma from the interval of length r. So I include a parameter so that the composition is associative, strictly associative. If I fix a parameter, for example, if I always use 1, I would have to reparameterize when I compose paths, and this would give me associativity only up to homotopy, right? In particular, note that if I look at the hom space between one point and itself, I get the space of based loops, right? So all loops based at the point B. Okay, is that clear? Given a space, I can associate a category enriched over topological spaces. So that's our first functor that we will consider. And this is the example I'm going to be concentrating on, the base loop space, right? And moreover, this is a topological monoid, right? Because composition gives you a continuous product here. Concatenation of loops. Okay. That's the first functor. The second functor that we are going to be studying is the cobar construction. So this is a purely algebraic construction which starts with a co-augmented differential graded co-associative coalgebra and produces an augmented differential graded associative algebra. Okay, so you start with a coalgebra and you produce an algebra. What do you mean? It's just a strict functor between categories, yeah. Yeah, on the nose, yeah. So let me recall the construction of this, and of course this is modeling some base loop space construction, but I will explain explicitly the relationship soon. This is purely algebraic. So how does this go? So you start with a differential graded co-associative coalgebra with a co-augmentation epsilon. So what's a co-augmentation? It's just a graded map from the ground ring to C, and it's a map of coalgebras, where the ground ring has the obvious coalgebra structure, zero differential, and so on. Okay, that's a co-augmentation. So how do I, given such a thing, I want to produce a differential graded algebra? Okay, so that differential graded algebra denoted by bold omega of C is going to have underlying module the free algebra on this C bar. Okay, so non-commutative monomials, the free algebra. What's C bar? C bar is just killing the image of the co-augmentation. You mod out by that. So in other words, taking the co-kernel of the co-augmentation and shifting the grading by -1. That's what this s to the -1 means. You just shift. Okay, if something was in degree n, now it will be in degree n -1. So you take the free algebra on that C bar, and then you define a differential here using the differential of C and the coproduct of C, right? So what's a differential graded coalgebra? You have a coproduct, a map from C to C tensor C, and you have this coproduct is compatible with the differential of the underlying chain complex, right? So you extend the following map, the following defined on a monomial of length 1, C. You take the sum of D and the coproduct with the sign here. You extend it as a derivation to the free algebra, right? You have monomials. If you define it on a monomial of length 1, you can extend as a derivation by taking a sum and applying it to each term. Okay? And the augmentation is just the projection to this copy of K. This is an algebra because you can multiply monomials, you can concatenate them, and you can check that the co-associativity property of delta and the fact that d squares 0 implies that this differential squares 0. Okay? So that's the cobar construction. That's the second functor we'll be considering. Takes a coalgebra, produces an algebra functorially. Any questions? Clear? Great. So now we have a third functor that we're going to be relating to these previous two. This third functor is the rigidification functor of Lurie, also introduced by Joyal. So let me quickly go back. Remember the first functor produced a topological category from a topological space. Now I'm going to be working at the level of simplicial sets. So I'm going to replace top by the category of simplicial sets, which is a combinatorial model for this model category of spaces, right? And then I'm going to do a combinatorial version of this path category functor. Okay, so let's go back. It's called the rigidification functor. It's described in the first chapters of higher topos theory. So let's set delta be the category of simplicial sets. Simplicial sets are just presheaves over the ordinal category. And by cat set delta, I'm going to denote the category of small categories enriched over simplicial sets. So these are categories in which the Hom sets have the structure of a simplicial set. And composition is a map of simplicial sets. Okay? So what's the construction here? Okay, so it's purely combinatorial, no topology. So we first define it on a standard simplex, and then we will glue these together. Okay, so on a standard simplex, the objects of your category will be given by the vertices of the simplex. Okay, those are the objects. And now between two vertices, I'm going to put as a Hom space the nerve of certain category. Right? So given a category, you can associate a simplicial set by taking the nerve, right? By taking composable strings of morphisms. So what's this category, Pij? So Pij is a category whose objects are subsets of the set from I to j, and each subset we require it to contain the first and last vertices. And then morphisms are inclusions. Okay? And you can note that this category is actually a Cartesian product of copies of the category 1, where 1 is the category with two objects and a single non-identity morphism. So the picture for these categories look cubical, right? Look like cubes. Okay? And then I can take the nerve of that and I will obtain a simplicial cube. So Cartesian products of delta 1 after I take the nerve. Okay? And that's what I put in the Hom spaces between I and j, this simplicial set. Okay? It's a subdivided cube. That's how we think about it. And then, how do we define C on a general simplicial set S? We glue these together. We extend as a colimit, right? And this is a colimit in simplicial categories. So you have to make sure these exist and so on. But yeah. This is the construction of the third functor that we're going to be relating to the previous two. Okay, so we have the topological version of this C called P, and then this algebraic cobar construction. And from understanding the relationship between these three functors, we will obtain some nice results of the kind I was talking in my first slide. Okay? Okay, so let's start by discussing the relationship between the first two, between paths and cobar. Okay? So this dates back to Adams. So let S of x at B be the Alexander-Whitney-DG coalgebra of normalized singular chains with vertices at B. So what does this mean? My simplices here, my generators, are singular simplices that map the vertices of your simplex to the fixed vertex B. Okay? So if X is connected, this will calculate the right homology, you can show. Okay? So, and you have the delta, the coproduct is the Alexander-Whitney diagonal map. Okay? And by C instead of S, I will denote the singular cubical chains on the base loop space. Normalized, of course. They have to calculate the right homology. Okay, so what's the statement? It was proven by Adams in the 50s that there exists a map of differential graded algebras from the cobar construction of this differential graded coalgebra to the cubical chains on the base loop space. This is always a chain map, and in particular it's a quasi-isomorphism if the space is simply connected. So in this statement, in some sense, it relates cobar to the path category functor, right? Because this is obtained by taking chains on the base loop space, and the base loop space is the monoid obtained by taking hom of this path category associated to X from B to B. Okay, so this is the first relationship. So what if the space is non-simply connected? So where was the simply connectedness assumption used in the proof of this statement? It was used in the application of the Zeeman comparison theorem of spectral sequences, okay, which has certain hypotheses, and these hypotheses are met when the space is simply connected. Okay, but that doesn't mean that the statement is not true for connected spaces. It was conditioned to apply a theorem, right? In fact, we proved that this map is still a quasi-isomorphism for connected spaces, but we do not use spectral sequences. However, we have to be a bit careful here. Why? Because when we start considering non-simply connected coalgebras that might have something at level 1, this cobar functor is not invariant under quasi-isomorphisms of coalgebras. Okay? So it matters what coalgebra model for the space we plug into this machinery, right? Or that we have to use a finer notion of weak equivalence. Okay? So what we show is that if you take the chains on a complex model for the space, in other words, if you have inverses up to homotopy for the one simplices, then this model calculates the right homology, the homology of the base loop space in the connected, possibly non-simply connected case. Okay? So we have to be a bit careful. The argument, the statement is true for connected spaces, but wait, if I take, for example, simplicial chains on a simplicial complex, it will not work. You need either to replace or to do some kind of group completion thing in order to get the right homotopy type. Okay, so I will come back to this, how we extend this result. Okay, that's the relationship between the cobar construction and the base loop space. Now let me explain the relationship between this rigidification functor and the path category functor. So this is in the first 2 or 3 chapters of Lurie, higher topos theory, what I'm going to say now. And it's basically saying this functor C is really modeling the path category functor. Okay, that's what I want to say mathematically. Okay, that these constructions that I was doing in the Hom spaces commute with the singular change functor. The combinatorial construction commutes with the singular change functor. So let me explain this more precisely. So if you take a space and you take the complex of singular chains on the space, then we have a weak equivalence of simplicial categories as follows. You first apply C to this simplicial set to obtain a simplicial category. That's weakly equivalent to just applying the singular complex functor to the Hom spaces of this path category. So sing of Px is a simplicial category obtained by applying this functor sing to the mapping spaces of the topological category Px. So what's a weak equivalence of simplicial categories? It's a map of simplicial categories inducing a weak equivalence of simplicial sets in the Hom spaces. Okay, so Lurie shows that this combinatorial construction is really modeling the path category construction. Okay, and there's a deeper statement behind this, that this functor C is part of an equivalent equivalence of model categories. Okay. In particular, we have a weak equivalence of simplicial monoids, right? I can look at my Hom spaces between one object and itself. On one side, I get a simplicial monoid, on the other one as well, and I get a weak equivalence of simplicial monoids. So I can, what is this saying? That this side is a combinatorial model for the base loop space, right? So I can take chains on both sides, and I get a quasi-isomorphism of differential graded algebras. So apply normalized chains, which I'm going to denote by Q delta. Takes a simplicial set, it outputs a chain complex. I do it in both sides, and normalized chains take weak homotopy equivalences to quasi-isomorphisms, and I get a quasi-isomorphisms of differential graded algebras. So this, I was not using n before, but n means normalized. But before I defined S star just to be normalized chains, so that's kind of a typo. But this is just normalized singular chains on the base loop space. So taking chains on this simplicial set gives you a combinatorial model, algebraic model for the base loop space. So how does this relate to cobar, for example? Okay. So how are C and cobar related? Right? So we want to get a statement of how the cobar construction of these singular chain complex is related to the chains applied to this simplicial set described by Lurie. How are they related? So in order to explain their relationship, it's useful to have a more concrete description of the mapping spaces of the rigidification functor. So the mapping spaces of the rigidification functor may be described in terms of necklaces. So what are these necklaces? So a necklace is a wedge of standard simplices in which this wedge means that the last vertex of the ith simplex is identified with the first vertex of the I plus 1 standard simplex. So you should have pictures like this in mind, right? Standard simplices glued together like that, okay? And each standard simplex in the necklace is called the bead of your necklace, okay? So what's the relevance of these necklaces? It's the following. So let me say something before, that the category of necklaces form a category in which the morphisms are maps of simplicial sets that preserve the first and last vertices of your necklace. They form a category. I use some notation here that I think I will not use. So Dan Duggar and David Spivak showed the following. Remember, given any simplicial set S, this construction of Lurie produces a simplicial category. So the Hom sets is a simplicial set. So that's a simplicial set. And the statement is that this simplicial set can be described as a colimit over the category of necklaces. So let me explain some notation here. So nec over X over S is the over category. So this means maps from a necklace to S. And this indices here mean that this map sends the first vertex of T to X, last vertex of T to Y. Okay, so it's necklaces inside your simplicial sets. Okay, so if I look at a necklace inside your simplicial set, then I plug in for each of these, I put in a copy of C applied to T, and I look at the simplicial set from the first vertex of T, that's what alpha T denotes, and the last vertex of T. And I glue these together, and that describes the simplicial set of the hum space between x and y. Okay? And you can check that these, for what you're really doing is that for each necklace inside S, you're putting a copy of a simplicial cube. Okay? So for some integer nt. Okay? So for any necklace inside your simplicial set, you put this simplicial cube, you glue these together, and this is how you obtain a more concrete description of the simplicial set of hums between x and y. Okay? Any questions up to here? Okay, so now that we have a description of the mapping spaces of the functor C, I want to relate to the cobar construction. Remember, it's starting to look like the cobar construction. In cobar construction, you had monomials of simplices. Now you have necklaces inside your simplicial set. Okay? So in order to relate these two functors, the most convenient way is to introduce the notion of a neclical set. So that sounds a bit awkward, but it's just a presheave over the category of necklaces. Okay? And neclical sets form a category in which, as usual, when we do this kind of constructions, morphisms are given by natural transformations of these functors. Okay? So my cells now are going to be given by necklaces. Okay? And I want to give a neclical set model for the base loop space. And when I take chains on this model, I'm going to get the cobar construction. So we define a functor Gothic K that takes a simplicial set, and now it outputs a neclical category. Okay? And we will factor Lurie's functor C through this new functor K. Okay? It will be more convenient to compare to cobar construction. So let's mimic the definition of Lurie, but using these neclical sets. So the objects of my neclical category is just the vertices of your simplicial set. And now what do I do in the hum sets? So for any necklace inside S from X to Y, I'm going to put a copy given by the a cell, given by the necklace T. So how do I do that? I just consider T as a neclical set by the Yoneda embedding, right? So any necklace T gives a neclical set. Just apply Yoneda, right? Take hums into T. And I think of these as cells that I'm using to describe the morphisms from X to Y. And the point is that these cells behave cubically. So associated to each T, so to each T, I can functorially associate a cube. Okay? And the chains on this neclical set given by gluing these cubes will correspond to the cobar construction. So let me say that more precisely. First, the statement that relates C and this K is the following. There's a functor T, which I call T because I'm thinking of this functor as a triangulation functor, that starts with a neclical set and produces a simplicial set, right? So again, necklaces can be thought of as parametrizing cubes, and cubes you can subdivide to obtain a simplicial set. So there's such a functor T, which induces a functor at the level of enriched categories by applying it hum-wise. And this C, Lurie C, factors through this new version of C in which your categories are enriched over neclical sets instead of simplicial sets. Okay, so I just factor it through this because it will be easier to handle for my purposes. I factor C through this new construction. Okay? Okay, so there's a lot of symbols here But that's why I drew pictures here. So if you don't follow these symbols, you can look at those pictures. Okay? I get dizzy with all these wedges. So the point of this proposition is to show why the cubical nature of necklaces. What's the relationship between necklaces and cubes? Well, the point is that the faces of a necklace behave in the same way as the faces of a cube. Okay? So what does that mean? Okay? So I suggest not looking at this. Let's look at this picture here. So what's a face of a necklace? So first, the dimension of a necklace is the sum of the dimension of its beads minus the number of beads. Okay? So by a face, or I should really say a co-face of a necklace T, I mean an injective map from another necklace T prime of dimension 1 less than T. Right? What's a face of a cube? It's an injection from a lower dimensional cube, a codimension 1 thing, into the cube. Okay? So let me show why the faces of necklaces behave cubically. So we have two kinds of faces, or of co-faces, just as in the cubical case, right? You can either plug 0 or plug 1, right? So we have two flavors of co-faces in necklaces. The first one are morphisms of this form, in which you include a face of a single simplex into that bead, right? And it's the identity everywhere else. Okay, so this is an inclusion maps in which includes this triangle as a face, as this particular face of this bead. It could also be the back face as well. That's another example. So this is one flavor of these co-faces. What's the other flavor? Well, you send two beads to one bead, right? As in this case. The shaded beads here go to the two shaded faces of this simplex. So that's the other flavor of these co-faces. Okay? And you can count, and for a necklace of dimension n, if T is of dimension n, you will have 2 times n minus 1 co-faces. Okay? So this is related to the fact that to any necklace T of dimension n, I can associate functorially a cube of dimension n minus 1, right? And the faces of the necklace T correspond to the cubical faces of your cube. That's what I mean by functorially. Okay? Good. So let me say something that you can see starting to see the relationship to the cobar construction is that these faces correspond to the boundary in the ordinary boundary of a simplex, right? And these faces correspond to Alexander Whitney terms, right? These two faces correspond to one Alexander Whitney term applied to the top cell of this bead, right? So you can see that the differential, or the faces of this neclical set, will be described in terms of Alexander Whitney and boundary faces of your underlying simplicial set. So one more thing. So there's a normalized chains function that takes a neclical set and outputs a chain complex using this idea. The boundary map will be given by alternating some of these co-faces as usual. And the statement is that, remember I constructed this neclical version of Lurie's rigidification functor. If I take the chains here on this neclical set between a point and itself, if I take the chains, I get something which is exactly the cobar construction on the simplicial chains. This should be an S, and that should also be an S. I'm sorry. The chains on the neclical model of S is exactly, it's isomorphic, not quasi-isomorphic. It's exactly the cobar construction on the simplicial chains of S. Okay? In the case when I have to assume that your simplicial set has a single vertex. Okay? But up to homotopy, every connected simplicial set can be reduced to this case. So what's the punchline of this? So remember, we had this weak equivalence of DGAs given by a result of Lurie, which related this C to the base loop space, right? And then I took chains on both sides, and I got a weak equivalence of differential graded algebras. That was implied by Lurie's theory, and I factored this C into a triangulation functor and a neclical version. And moreover, I had this isomorphism, which I explained before. And using all these three facts, I get what I wanted to show, that for any connected space X, there is a weak equivalence of differential graded algebras from the cobar construction of the singular chains functor and the singular chains on the base loop space. Okay? However, it looks like I'm moving things around. There's some content here, which is the proof that the Lurie's statement that relates C to the path space or C to the base loop space, right? That's where all the content is going, right? And then some categorical and combinatorial manipulation gives you this result, okay? So this was work with Mahmoud Zainalian, but we wanted to make a statement which did not rely on Lurie's theorem, on Lurie's theory, right, of higher categories, because this should be able, we should be able to prove this with just with classical algebraic topology tools, right? And that's the content of a next article with Saneblitze from Tbilisi. And the statement that we prove is the following. So this statement only uses classical algebraic topology, okay? The proof of it. So that's what I just said. So to any connected simplicial set S, we associate functorially a commutative diagram of the following form. So this omega hat S and omega P of S are neclical sets. The hat here means that this process involves some either can replacement or group completion kind of procedure in order to get the right homotopy type. Okay, that's what the hat means. Because I'm starting with a general simplicial set S and not singular chains on a space. This is a statement for a general simplicial set S. Okay, so the hat means that you invert one simplices, you obtain neclical sets, these pre-sheaves on the category of necklaces. Associated to each neclical set, there's a geometric realization obtained by gluing the cubes corresponding to each necklace. And the statement is that we associate a diagram like this. On the right-hand side, you have the path fibration, which has as fiber the base loop space on the geometric realization of your simplicial set. And omega, we prove that P, we construct a map P, which is a homotopy equivalence, and we prove that omega, there's a map omega, which is also a homotopy equivalence, and moreover, it respects the monoidal structure, because omega of S is not only a neclical set, but it has a monoidal structure. Okay? And how do we prove that omega is a homotopy equivalence? We use a classical tool from algebraic topology, and is that we showed that this sequence of maps of spaces is a quasi-fibration. Okay? Okay? No, you don't have to show it's a fibration. You show only it's a quasi-fibration, meaning that the fibers are homotopy equivalent to the homotopy fibers. We use this criteria, the classical criterion of Dold and Thom, to show that, which you can show it locally and paste them together. And then quasi-fibration have long exact sequence of homotopy groups. So we showed that this object, the space, has the homotopy type of the base loop space. But the chains on this object correspond to Adams cobar construction, or a generalization of Adams cobar, because I have extended by adding inverses here. So this is a cubical cell complex now. So we obtain a combinatorial model for the path fibration, in which the cells are cubical, and moreover, the cubical chains here correspond to a generalization of the cobar construction. Okay, so this is a self-contained paper also in the archive, and there's no higher categories, no infinity categories. But in the other paper with Zainalian, we place it in this context of higher categories of Lurie's. Okay, great. So some consequences of these statements. So first of all, Lurie gives a model structure in simplicial sets in which the fibrant objects are quasi-categories, okay, are models for infinity categories. The weak equivalences in that simplicial set, in that model category, are essentially maps of simplicial sets which induce maps of simplicial categories after the application of this rigidification function. Okay, and we kind of mimic this in the algebraic side, right? We say, let's make a new definition of a weak equivalence of coalgebras to be a weak equivalence if it's an omega quasi-isomorphism, meaning if it's a quasi-isomorphism after applying the cobar functor. And with this new definition, we have a map, which is a functor, which is the chains functor, that sends first weak equivalences of simplicial sets, weak equivalences to quasi-isomorphisms of coalgebras. That's classical, right? If you have a weak equivalence, it goes to a quasi-isomorphism of Alexander-Whitney coalgebras. But moreover, the categorical equivalents on this side go to this new omega quasi-isomorphisms. Okay, so behind this, there's a Quilling functor relating two different model categories. Okay, and this statement is a beginning to what I said before, that we are interested in understanding the algebraic nature of spaces, relating the model category of spaces to a model category of algebraic objects. So I expect that if you enrich this side with like some E infinity data, then you might get something closer to an equivalence here. Okay. Another application is, so Lurie shows that C sends weak equivalences between Kant complexes to weak equivalence of simplicial categories. This fact is not true if I take arbitrary simplicial sets here. And this gives us also a statement I mentioned at the beginning, that if I use any Kant complex model for a space, and I take the cobar on the simplicial chains of this Kant complex model, then I get the right homotopy type of the base loop space. The right homological type, I should say. Right? So if you want to obtain a model for the base loop space, make sure you use chains coming from a Kant complex model of your underlying space. Another application is the following, which is very nice, I think, and we obtain it very naturally. So we had this functor K, which takes a simplicial set and now puts a category enriched over neclical sets. So this functor was factoring Lurie's functor C through this new category of categories enriched over neclical sets. And then, given a category in which the hum spaces are these neclical sets, I can take chains hum-wise to obtain a DG category, right? So you have these neclical sets on the hum spaces. You take chains on each hum. Now the hums are chain complexes. So you obtain a DG category. So this composition of functors, it turns out to be a strict left adjoint to the DG nerve functor of Lurie, which goes the other way. So you can use actually this functor to define the DG nerve. And it's much more natural to use the simplicial than to use the simplicial version of Lurie, because then the adjunction is not satisfied strictly. Okay, so that's a nice application. And moreover, using this, we can show that certain definitions of infinity local systems are equivalent. So what's an infinity local system? Sometimes defined as a functor from infinity categories from a space to chain complexes. Or it's also sometimes defined as a DG module over chains on the base loop space. But since chains on the base loop space is now equivalent to cobar, we can use cobar. And using this fact, we can show the equivalence of these two definitions in a one-line proof. And moreover, this is a point I want to stress, is that this definition of local systems is very nice because this is a purely algebraic construction, right? And now you can use, you can bring in tools from homotopy of algebraic structures, such as Koszul duality, to study local systems. For example, there's a statement related to Koszul duality that says that modules over cobar of a coalgebra, that category, that triangulated category, is equivalent to comodules over the underlying coalgebra. Okay? So this kind of Koszul duality can be used now to study infinity local systems. Like, these statements open up this possibility. A final statement is that we obtain a model for the free loop space. So what's a free loop space? Is the space of loops, but the base point is not fixed now, right? And Goodwillie constructed a quasi-isomorphism from chains on the free loop space to Hochschild chains on the algebra of chains on the base loop space. Okay, but now I can replace these guys here by the cobar construction, because I showed it's equivalent even in the connected case. And there's this algebraic statement by Catherine Hess that says that Hochschild chains on the cobar of a coalgebra is quasi-isomorphism, it's a chain complex quasi-isomorphic to this co-Hochschild construction on the coalgebra C. Okay? And from this fact, I can use now C to be singular chains on your space, that coalgebra with Alexander-Whitney coproduct. And I combining these two facts, the fact that I have a cobar model for the base loop space, even in the connected, non-simply connected case, I obtain the following corollary, that the chains on the free loop space, even when X is connected and non-simply connected, can be modeled by the co-Hochschild chains on the Alexander-Whitney coalgebra of X. So this means that this purely algebraic construction of co-Hochschild, when applied to that coalgebra of singular chains, gives you the free loop space, and this model is smaller than this huge thing of Goodwillie here, right? So for example, an application would be, let's start to recover string topology using this smaller model. So Eric Malm tried recovering string topology using this model, and he had some difficulties, but I think this is more natural now to recover intersection type operations here. So that's it. Thank you for your...
Any questions? So for this last step, you will be using a version of Koszul duality.
Yeah, that's a Koszul duality. Yeah, This is called duality here, which is cool.
Any other questions? Well, thank you very much.
Thank you.
Well, see you next year.
Thank you. Thank you.
I think preliminary location is Campeche, but we'll see when you get